Okay, we're rolling. Welcome to Physics 120. This is our first lecture. We're going to talk about kinematics in one dimension. This is the beginning of chapter 2. So kinematics is a description of an object's motion. The next couple chapters we'll be talking about forces, which are how we cause an object to move. So right now we're just concerned about how something moves instead of why. So we're going to talk about some key definitions. Distance, displacement, so they are related, but we'll talk about the distinction shortly. Speed and velocity, we'll talk about their similarities and what separates them from each other, and acceleration. So first we have to talk about two types of quantities we deal with in physics. Those are vectors and scalars. So a scalar is a quantity that we can sufficiently describe using just its magnitude, right? It's just a number, it's a quantity, so that's what a scalar is. A vector, we have to use both its magnitude and its direction to describe it. So the magnitude, again, is the number or the value associated with some quantity, but a vector has a direction, so we have to describe the direction that a vector is pointing, usually in terms of Cartesian coordinates, right? The x direction, y direction, or a compass heading, right? Cardinal directions, we can talk about north, east, west, south, something like that. So once we get into two-dimensional motion, these descriptions will be a little more specific, but in this section we're talking about one-dimensional kinematics, so we're going to be talking about just the positive x direction or the negative x direction. So if you draw your xy plane on a piece of paper, to the right is going to be the positive x direction, to the left is going to be the negative x direction. And I'll have a couple diagrams and situations that use that convention. So some examples of vectors that we're going to be using in physics are position and displacement. Again, those two terms, they're under the same bullet because they're related. Velocity is a vector, acceleration is a vector, and force is also a vector. There are some other vectors that we'll see later on in the course. Some scalars are distance, speed. So we're starting to see the difference between, you know, distance and displacement, speed and velocity, stuff like that. That's basically one of the things that separates the two. Time is a scalar, mass is a scalar, energy is a scalar. There are some other ones out there, temperature, things like that. So they can be sufficiently described with just a number. And scalars are always positive. We're never going to have a negative time, a negative mass, negative energy, nothing like that. So a scalar is positive. A vector could be positive or negative depending on the direction it points. So displacement is the change in an object's position. All right, so we're going to use the capital delta to denote change in. All right, if you remember maybe from your algebra classes, you used a delta x and a delta y when you were talking about the slope of a line. So this might look familiar to you. We're going to use the variable x to describe an object's position with respect to the origin on the xy plane. Okay, and so displacement is the change in an object's position. So it would be the difference between an object's final position and its initial position. So we're in physics class. We're going to be dealing with SI unit of meters. So meters is our SI unit for position and displacement. And we're going to talk about the difference between distance and displacement momentarily. So in order for me to change my position, in order for me to undergo some displacement, it's going to take me some time to do that. And so I have to know, or I have to be able to find out how much total time it takes me to change my position. So we have to define a time interval, right? A change in time, delta t. So that's t final minus t initial. The SI unit for those are seconds. In a lot of occasions, t initial will be 0, right? When we start like a kinematics problem, t initial is often 0 because that's when we start recording time, right? We're concerned about an object's motion, but we're concerned about it over this time interval, and so usually we'll say, well, let's start recording at t equals 0. So this delta t, what I'll do later is I'll probably end up just dropping this delta t in a lot of equations because we take t initial to be 0 most of the time. So it's a scalar. It doesn't have a direction. It's always going to be positive. So that's something to think about. So time will always be positive. If you're looking at some kinematics problems and you end up with a negative time, we got some issues. All right. So here is an example of differentiating between distance and displacement. So we have 4 objects, A, B, C, and D, and they undergo some displacement, but they also travel some distance. So we're going to use the definition of distance and displacement to determine these quantities. So I'm looking at the diagram. We want the total distance traveled by object A. Now this is pretty straightforward. Object A is going to start at, we'll say this is the positive x-axis. Object A starts at x equals 0 and it ends at x equals 7. Right? So that's the length of the path that object A travels. Good. We've got a total distance of 7 meters. That's great. Object B, the length of object B's distance traveled is 5 meters. Object B starts at 12 meters, ends at 7 meters. We see it's kind of between the 6 and the 8 here, right? So the total length of this path traveled by object B is 5 meters. Object C does something a little funny. Object C starts at 2 meters, it goes to 10 meters, and then backtracks to 8 meters, and then goes back in the positive x direction to 10 meters. So what we do when we're looking for the distance of some object that behaves this way, we're just adding up the total path lengths. So the first path that object C travels is from 2 meters to 10 meters, so that's 8 meters. Then when it backtracks, it's still traveling a positive distance of 2 meters. So we add that 2 meters to the original 8 meters, changes direction again, travels another 2 meters, but again, we're talking about distance, so we're just adding up these path lengths. So 8 plus 2 plus 2, we've got a total distance by object C of 12 meters. So this is going to be different when we look at the displacement of object B, or object C. Object D does something a little bit similar to object C. It's going in the next negative x direction originally, but that's okay. We're not concerned with that. We're just concerned with displacement or distance for the time being. So it starts at 9 meters, travels in the negative x direction to 3 meters. So the first distance object D travels is 6 meters. Turns around, moves in the positive x direction from 3 meters to, it looks about 5 meters. So we're going to say that the second distance object D travels is 2 meters. So again, we add up those distances, 6 meters plus 2 meters, we've got a total distance of 8 meters. So now we're going to look at the displacement of each of these objects. For object A, its distance is the same as the displacement. So we're using this delta x formula from a couple slides back. So we're going to take object A's final position, subtract it from its original position. So its final position was at the 7 meter mark. Its initial position was 0 meters, the origin. So 7 minus 0 is positive 7. Right? So it's a positive displacement. And we see that it's the same as the distance. Right? So distance and displacement can be the same, but they're not always. Object B, the displacement is the final position, which is 7 meters minus 12 meters. So we see that the magnitude of the displacement is the same as the distance, right? It travels 5 meters, but displacement is a vector. So since object B is traveling in the negative x direction, this formula gives me a negative sign, right? If I do final minus initial, I've got a negative sign associated with object B's displacement, so that tells me it traveled 5 meters in the negative x direction. So that's the magnitude. The negative sign tells me the direction of object B's displacement. Object C and D, they do that funny thing, right? They go in one direction, turn around, go back. So we're concerned with the net displacement. We're concerned with the total displacement of object C. Now we know it traveled a distance of 12 meters before, but we're just concerned with its total change in position. So we take object C's final position, which was 10 meters, and then we subtract the initial position from it, 2, and we see that it underwent a total displacement of positive 8 meters, right? It started at 2 meters, it ended at 10 meters. All this stuff that happened in between, we acknowledged it when we calculated the distance, but when we're talking about displacement, we're just talking about how far the object went total and in what direction. So we take the final position 10 meters minus 2 meters. We've got a net displacement of positive 8 meters. It's positive. The net displacement is in the positive x direction, which is good, but it's different than the displacement. Object D, similar thing. We know that the total distance was, refresh my memory here, 8 meters because we added up the total path lengths. But the displacement is different. The displacement is going to be negative. Object D starts at 9 meters and it ends at 5 meters, right? So its displacement is in the negative x direction. Also, we use the formula final position 5 meters minus the initial position, right? So 5 meters minus 9 meters is negative 4 meters. So 4 meters tells me the displacement, right? It went from here to here. That's the magnitude of the displacement. The negative sign tells me that the object traveled in the negative x direction. So distance, we're just adding up the total path lengths, right? We add up how far the object went in both the positive x and the negative x direction. It's a scalar. It's always going to be positive. It's just the sum of the individual path lengths. Distance, we're going to use this formula. If we get a negative sign, we know the displacement is negative. We're simply taking the final position and subtracting the value of the initial position from it. We get the net displacement. And the negative sign or the positive sign that we inherit from this formula tells me the direction of the object's displacement. So I have to move, right? I've got to travel some distance, or I have to undergo some displacement, and I have to do it in some time interval, right? When I get in my car and I hit the gas and I drive to Scranton, I'm traveling down the road, I'm traveling a distance, I'm undergoing a displacement, but it takes me time to do that. It takes me time to do that. So when I'm doing that, when I'm undergoing that motion, I have a velocity, right? I have a velocity. So as I travel some displacement, right, I move some delta x, and it takes me some time to do that, I have a velocity, right? So I'm going to call this average velocity, that horizontal bar above the variable v tells me average. So there are two types of velocity. There's average, there's instantaneous velocity, right? The velocity at some point in time. We're not concerned with instantaneous velocity. That involves some calculus. This is an algebra-based course, so we're just going to talk about average velocity. So the definition of average velocity is displacement over time. So we look at these units, right? Position or change in position is in meters, time is in seconds. So this is a ratio, right? Meters per second. My speedometer tells me my velocity. It doesn't exactly tell me my velocity fully, but it gives me the magnitude of my velocity because my speedometer tells me how fast I'm going in miles per hour. Okay, so I could look up some conversions. If I wanted to figure out what my velocity was in meters per second, I could convert the miles to meters, the hours to seconds, and then I'd have a velocity in SI units. Usually I try to just stick with SI units, but again, this is a ratio. This is a rate of change of displacement over time. So velocity is a vector. If you notice, time is always a scalar. We've noticed that we have positive and negative displacements. So this sign, or the sign of this top term, could be negative. This will always be positive, right? So velocity is a vector. It has a direction too. Right now we're living in one-dimensional kinematics, so it'll either be in the positive x direction or negative x direction. Speed and velocity are different. Sorry about that. Speed and velocity are different. Speed is the total distance I travel with respect to time. Distance is always positive. Distance is a scalar. We saw earlier in the last example. Distance is positive. Time will always be positive. We have the same units. But it is a scalar, so it will always be positive. Okay, so watch for that. You'll see in some, especially like some WebAssign examples, you know, it'll just sneak that word speed in on you, and so watch out for this, because they're not necessarily asking for the velocity. Sometimes you'll be asked for the magnitude of the velocity. So solve for the velocity and then you just drop the negative sign. That's the magnitude of the velocity. So just watch out for that language. That can creep up on you a little bit. So I don't always move with the same velocity, right? I got in my car, drove to Scranton. To get on the highway, I had to change my speed from 35 miles an hour to 55 miles per hour, whatever the speed limit is. So in order to do that, I had to hit the gas, right? I had to hit my gas pedal. My velocity changed, and it took some time for that velocity to change. So if I'm changing my velocity, I'm taking some time to change my velocity. I have what we call an acceleration. Okay, so acceleration is the rate of change of an object's velocity with respect to time. Velocity is the rate of change of an object's position with respect to time. So my units here, I've got meters per second on the top for velocity. I've got seconds on the bottom for time. I've got meters per second. That's meters per second squared. So I'll do an example where I just kind of show how that comes up. Okay. So SI units are meters per second squared. Acceleration is the rate of change of velocity with respect to time. So delta V is positive or negative. It's a vector. Time is a scalar. So I've got a vector divided by a scalar. That's going to give me another vector. So acceleration is a vector quantity. There you go. It's a vector quantity. So some things happen with acceleration. So I want to talk about various cases on how acceleration may change our direction, or acceleration may have a different sign than the velocity. So we're going to start off with the first case. Easy case, right? I'm traveling in the positive x direction. My velocity is in the positive x direction, so I'm moving to the right. If my acceleration is also to the right, my acceleration is also in the positive x direction. Think about me hitting the gas, trying to get onto the highway. The object is increasing its speed. Okay, so if the acceleration and the velocity are in the same direction, the object is speeding up. Okay, so this goes for the negative x direction too, right? If I have a velocity in the negative x direction, I have an acceleration in the negative x direction. I'm speeding up in the negative x direction. So as long as my velocity and acceleration vectors are pointing in the same direction, then I'm increasing my speed. I'm speeding up. So let's go back to a velocity in the positive x direction. If I have a velocity in the positive x direction to the right, and I have an acceleration in the negative x direction to the left, what does this mean? I'm slowing down, right? How do I have an acceleration in the opposite direction of my velocity? So I have to be hitting the brakes, right? I'm driving a car, I have to be hitting my brakes. So my acceleration is in the negative x direction, my velocity is in the positive x direction. That means I'm slowing down. And if I keep doing that, right, if I continue to apply the brakes on my car, I'm going to slow down, slow down, slow down, and then eventually come to a stop. If I switch the signs of both of these vectors, right, my velocity is in the negative x direction, right, I'm moving to the left, and my acceleration is in the positive x direction to the right, I'm still slowing down, right, I'm accelerating in the positive x direction, but my velocity was in the negative x direction, so my speed is decreasing. So a negative acceleration doesn't necessarily mean that I'm slowing down, it just depends on the relationship between my velocity and my acceleration. Alright, so some things to look at when we start talking about using the kinematics equations and substituting vector quantities into our equations. We're solving for something. Typically, as long as we keep our signs straight, all the math will kind of do the heavy lifting for us. Alright, so I hope everything's going well up to this point. This is my first attempt at recording. I've got kind of limited technology at home, so I hope everything's going well up to this point. And we're just kind of making do with what we have. So I put this slide in. What I usually do live is I do this, I'll do kind of a thorough derivation of these equations. There's a very, very beautiful derivation in the textbook I'm sure everybody has seen. But these are my four main kinematics equations. And the reason I picked this picture, I picked this image, because now the subscripts might be a little bit different. So we'll talk about these subscripts and how they look different than the convention that I use and that the textbook uses. But I picked this image because I like this little information that's given, right? So all of these formulas depend upon certain variables that we have to know, right? We have to know a certain number of quantities in order to use the kinematics equations. So a lot of them are pretty straightforward as far as, they're missing one variable. A lot of problems, it's just, here's a quantity you need to find, and here's everything else. So the first equation is missing displacement. It's missing delta x. V, we're going to call V final. Right? So in your textbook and in a lot of my examples, I'm going to call that V sub f for V final. V naught, V sub 0, I'm going to call it V initial. So it's going to look like V sub I. When I write out my kinematics equations, naught, I'm going to use initial, and right here is going to be a V final. So all these V's, I'm going to call them V finals. All these V naughts, I'm going to call V initial. So we've got a final velocity, we've got an initial velocity, acceleration, and time. So if I don't know the displacement of an object, this equation can come in handy. So this equation, I tend to forget about a lot, but it's very useful in a lot of situations. So we don't have the acceleration of the object. We can't use this solely to solve for the acceleration of the object. But this is our very first kinematics equation. Okay, if you remember when you were doing an algebra word problem in high school, something like this, I always called this the DIRT equation. So distance equals rate times time, right? In our math word problems, distance is rate times time. So the reason this is useful is, and I'll go back up a couple slides. So I'm going to look at the definition of velocity. Velocity is displacement with respect to time. If I multiply both sides by delta t, I have delta x is velocity times time, right? And that's my DIRT equation. That's my distance equals rate times time. But now we are expressing it as a vector quantity. So I'm going to go back down here. This is actually a variation of that equation. Okay, this is V final, this is V initial. This is actually the average velocity, right? Take the average of two quantities, we add them up, divide them by 2. So what happens is, what if I'm not changing my velocity? If I'm not changing my velocity, V final is equal to V initial. So V final plus V initial would equal 2 times V, right? V initial and V final are the same thing. We call them V. We'd have 2 times V in the top. 2V over 2 is just V. And so delta X is velocity times time. So the reason I have the kinematics equations in this form is that it covers both scenarios. It covers instances where I'm not accelerating. Acceleration is equal to 0, and we'll go through some examples of that. Acceleration is not 0, and acceleration is 0. So these kinematics equations will handle both scenarios. Either my velocity is constant or my velocity is changing. So here, equation 3, this is my V initial times time. Again, these formulas are actually derived from calculus. This is how we arrived at these equations. We won't go into how that occurred, but all of these terms, right? This is my V initial t term, right? So if we look at this part of the equation, it kind of looks like this, right? If V's not changing, right, this quantity would stay the same. If V is not changing, my acceleration is 0. So I've got this 1/2, I've got this a, this t squared. If acceleration is 0, this whole thing goes to 0. Okay, it's missing V final. But if I have a constant velocity, this V initial stays the same. And so I'm left with the dirt equation, right? Delta X is V times t, which is this right here. Right? So if I'm not accelerating, both of these equations will evolve and become my definition of average velocity, constant velocity, delta X over delta t. But these equations, you can also handle changing velocities, right? So if I have an acceleration, this term will not be 0, okay? This term will not be 0, and this term will also change the displacement, right? So this term will be some number, it'll change your displacement. This will also be some number, will also change your displacement because you're accelerating, right? You're moving with the speed, but your speed is also changing, so you have an acceleration, okay? Final equation, we've got a change in velocity, right? V final, V initial. This is dependent upon the displacement and the acceleration. I'm missing t, right? So these little statements here, this tells me I'm missing this variable in here, which means if I know this value, I can't use it in this equation, and I can't use this equation to solve for this variable. So all of our kinematics equations are going to kind of be used in tandem with some of these problems. So we're definitely going to be using more than one at a time. We're going to be doing a lot of algebra. We're going to be taking some equation, maybe solving it for some variable even though we don't know it, and then maybe substituting it into another one. So the goal of this first section is just getting comfortable with the algebra behind these equations, knowing when we can set two terms equal to each other, solving for a variable, substituting it into another equation, things of that nature. So I'll try and give you some examples where that occurs. All right, physics, it's all about solving problems, right? We got to solve a problem. Most of them are pretty contrived to where you're able to arrive at a solution. So there's, you'll always be able to solve a physics problem in this course. First thing I like to do, I'm never was really that good at art, but I try my best to draw a diagram of what's happening in the situation. Now, a lot of these problems, objects are going to change their behavior, right? They're going to be moving, then they're going to come to a stop, maybe they're going to change direction. Maybe I'm going to have more than one object, right? One object is accelerating, one object is moving with a constant speed. They're moving towards each other, they're going away from each other. All kinds of different scenarios. So your best bet is the first step is draw a diagram, a picture to kind of help you visualize what's happening. Usually they kind of they'll give you enough information to where you can identify variables that you know. So one thing to look for, if they don't specifically say, an object undergoes a displacement of 4 meters in the positive x direction. So it'll be clear like that sometimes, but sometimes you'll kind of have to read the problem and make some deductions of your own. So a lot of common things that I see in algebra-based physics problems is we'll say an object accelerates from rest. Right? If I'm accelerating from rest, what can I gather from that? First, I know that there's going to be an acceleration. Either they're going to tell me the acceleration, or I'm going to have to solve for it. Right? I'm accelerating from rest. What does that mean? V initial is 0. Right? If I'm accelerating from rest, I'm initially stopped. So I can assign a value for V initial. V initial equals 0. So watch out for that. Another common phrase we see is an object comes to rest or comes to a stop, something like that. So if you see that phrase where they're describing an object that's coming to rest or coming to a stop, we can say that the final velocity of that object is 0. Right? If I'm coming to a stop or coming to rest, we also know I'm accelerating, right? I'm slowing down, so I'm going to have an acceleration. If I'm coming to rest, my acceleration should be in the opposite direction of my velocity. Also, I can say V final is 0. So watch out for that. So there are going to be a lot of known variables that aren't explicitly stated, but reading the problem, we can extract a little more information. Identify what's being asked, right? They're gonna tell you to do something at the end of a problem or ask you to find some quantity. So identify what's missing and find out what you're trying to solve for. So once you have steps 2 and 3, you've got your known variables, you've got your unknown variables. Look back at your kinematics equations, okay, and identify which equations are going to be necessary to solve the problem. Right? So we've got our knowns, our unknowns, we've got our equations, we've got what each equation is missing. Right? What is each equation missing? What are the restrictions that I have for each of these equations? Which ones are going to be applicable and which ones aren't? Now, in a lot of cases, step 5 is very important. So I have a very particular process on how I like to do this. This is the algebra part of my process. Okay, I'm going to solve the equations that are relevant for the unknown variable. I'm a firm believer that it's good practice to take those equations and solve for the unknown variable first. Okay, don't substitute any values in until you solve the relevant equation for the unknown variable. Okay, this helps me reduce my mistakes. Okay, I start plugging in numbers with negative signs. I hate negative signs, but they're a fact of life, and I want to avoid missing those negative signs when I do my substitution, when I start plugging in my numbers. So if I have a nice expression for the variable I'm looking for without numbers and units and all kinds of crazy stuff substituted, it looks a lot nicer. Okay, so what I'm going to do is I'm going to say this solve for the unknown. In a lot of cases I'll say like derive an expression, right? Make an expression for A, acceleration, or the final velocity of the object. So I want us to get comfortable doing the algebra with the variables first. Okay, and then wait until the very end, wait until you have that variable solved for, and then substitute all those values. So I'll show you in my examples how I do that. I also like to substitute the units in as well, not just the numbers, mainly for the sake of notation, but also to make sure that my units are coming out appropriately. So if I'm solving for a displacement and I plug all my numbers in, and then I get units of meters per second, I get velocity units back, but I'm solving for a displacement, I know that I made a mistake somewhere in my process and I need to go back and find it. Finally, this is a very important step. a jogger runs probably like 4 meters per second. So if I'm doing a problem where there's a runner or a sprinter or a human walking or running, and I get a speed of 40 meters per second, I know I did something wrong. Okay? If I get a speed of 300 meters per second, that's like 3 football fields roughly per second, and I'm doing a problem about a car, I know that's probably not a practical solution to my problem. So look at the actual numbers, compare it to the situation, and say, is this practical for this object to be traveling with this speed? So just a real quick thing, I like to cheat, use Google. So let's do this. Miles per hour to meters per second. Right? So we use English units in everyday life, right, in the United States, unlike the rest of the world. So just a real quick Google search, right? Take a car going 60 miles an hour. That's a reasonable speed for a vehicle, right? So if I get something like this for a human or an airplane or something like that, I know I'm kind of off in my calculations. Okay, so last step, always look at those values that you're looking for and check to see if they make sense. Alright, so I'm not exactly sure how long this video is, or even if it worked. Great. So what I'm going to do is I'm going to stop this video, because I don't think posting hour, 2 hour long videos is going to be a good idea. So I'm going to try and keep them short. So I'm going to split this up. The rest of this presentation is going to be in another video. So I'm going to separate it, maybe try and separate it like intro video and then problem video or something like that. So I'm going to hit stop. I'm going to record a new video that has the last 4 or 5 slides of examples. So I'm going to upload this. Hopefully everything works, and then we'll keep rolling. All right, thanks.